Okay, so the most delicate convergence test that we're going to cover is called the integral comparison test. This is going to be an extraordinarily useful tool to do much more than just test for convergence. All right? So what we've got here is a sequence of positive numbers that is monotonically decreasing. It needs to be monotonic decreasing. And we need to find a function, f of x, that is also monotonic. It's got to be decreasing because of this condition, and it must be continuous. So f of k equals ak for all k. All right? And so now what we're going to do is look at a graph of this function. All right? So here's my y equals f of x. F of x is decreasing. Okay? And that means that these boxes here are always going to be above my function. All right? These boxes have width 1. So this height is an plus 1. All right? The width is 1. So this area in here is an plus 1. The area here is an plus 2. And so on and so forth. So the box area is equal to the sum from k equals n plus 1 to m of ak. Now, clearly, the box area is larger than the area under the curve. All right, that comes as a consequence of the decreasing nature of my function f of x. So the box area is greater than the area under the curve. The area under the curve is the integral from n plus 1 to m plus 1 of f of x dx. All right? Now that's only a single inequality, a two-sided inequality. As we've seen, that's not really what we want. We need another side to this inequality. The way that we're going to do that is by shifting the boxes left. We shift them 1 unit over to the left. All right? Clearly, that won't change their area. So it's still the same boxes. We just moved them to the left. But now they're underneath the graph. They're underneath the function. So this same boxed area must be less than the integral from n to m of f of x dx. And now we have a three-sided inequality of exactly the same form that we saw with the limit comparison test. All right? So we immediately have the same conclusion. The improper integral and the infinite series must either both converge or both diverge. Very simple. However, this contains far more information than just that. Okay? So, as an example, let's suppose that we wanted to estimate the value of this series. All right, the harmonic series with 1,000,000 terms. So the sum of the reciprocals of the first 1,000,000 natural numbers, right? So what we're going to do is we're going to add up some of these numbers explicitly in the harmonic series, and then we're going to use the integral comparison test to approximate the rest of the sum. All right? So let's look at H100. All right? You can calculate in Mathematica H100, and we find that it's 5.1873775 just like that. I'm not going to need that many digits, but anyway. All right? So that's H100. That was just the sum of the first 100 terms. All right? That's 1/10,000th of the number of terms that I wanted to add. Okay? So how am I going to get the rest of them? Well, I'll say the rest of the terms, that's going to be the sum from 101 to 1,000,000, 1 over k. The integral comparison test tells us that this is less than the integral from 100 to 1,000,000 dx over x, and greater than the integral from 101 to 1,000,001 dx over x. So I would have the natural log of 10 to the 6th plus 1 divided by 101 is less than this remaining piece, is less than the natural log of 10 to the 6th divided by 10 to the 2, which is 10 to the 4th. All right? And so now, in order for me to estimate h 10 to the 6th, I just have to add this piece. All right? And if you do that, in Mathematica, you'll find that the left side is 14.3878, and the right-hand side is 14.3977. And that's pretty good. We're off by about 0.01. All right, that's the window that we've got. And so we only summed the first 100 terms, but the integral comparison test has provided an excellent estimate for the sum of the remaining terms. Moreover, this error that we got is essentially independent of the upper bound. We added up to 1,000,000 and we got an error of 0.01. Had we added up the first 1,000,000,000 terms, we would also have an error of 0.01. We'll get an error of 0.01 for any number of terms we choose to add, as long as it's large. Okay? Now this immediately gives us information about the divergence structure of the harmonic series. Hn lies between, well, let's see, it's going to be 5.187. I'm going to go ahead and do 4. My error is 0.01 anyway. I don't want to write all those numbers. All right, and then it's going to be plus the natural log of n minus the natural log of 100. And then on the left-hand side, we'll get 5.1874. And then it's going to be minus the natural log of 101 plus the natural log of n plus 1. All right? Now we can work those out and see that the left-hand side gives 0.572 plus the natural log of n plus 1. The right-hand side gives 0.582 plus the natural log of n. All right, and that's the reason why we indicated earlier that the harmonic sequence behaves like the natural log of n as n grows, right? In fact, we can use this estimate to extract the divergence in the harmonic series. Sort of an interesting manipulation. So we'll consider again a graph of our function, in this case 1 over x, all right, in our boxes. Now here, instead of starting at 1, or sorry, instead of starting at n, I'm going to start at 1. Okay? And I'm going to go all the way out to n. Okay? This is just n. All right. So, if I were to take hn and subtract from it the integral from 1 to n plus 1 dx over x, let's see what that gives. Well, hn is just going to be the area of the boxes. The integral from 1 to n plus 1 dx over x is going to be the area under the curve. So if I subtract, then I'm going to get these little areas. All those little areas. Now, fairly obviously, each time I increase n by 1, I'm going to add a little bit more to this sequence. All right? So this sequence, if I were to name it, gamma n is monotonic increasing. You can see that just directly from the graph. If I increase n by 1, it's going to add more area. So it's monotonic increasing. Interestingly, it's also bounded. The way that we can establish that is by sliding each of these pieces to the left. And as you can see, if I do that, all of them will fit inside the first box. All of them. It doesn't matter how many I slide in. There'll always be room for the others underneath because that's where they're coming. All right? So for that reason, gamma n, the sequence here, is also bounded. Therefore, as we saw earlier, this sequence must converge. The number that it converges to is a very prominent number in number theory and in special function theory. We're going to see it in a lot of different places. It is called the Euler-Mascheroni constant. The Euler-Mascheroni constant. All right? And this is just an example of a divergence that we could extract from a divergent series. We pull this divergence out, and what we're left with can be very useful in a number of places.